So the first thing you do, assuming you're going to calculus 1, is limits. And when they first start talking about it, it's going to look intimidating, but it's not. So I'm going to show you how to do it. And I'm going to leave the deep theory to your calculus professor, okay? Assuming you're good. But I'm going to show you in a nutshell, what does it mean? How do you solve these problems? And once you see it, it's not too bad. So let's first talk about one-sided limits. Okay, let me find a good example here. All right, so given this picture or graph, this is 1, this is 2, this is some random number x naught. Okay, so right here, you have a function, probably a piecewise if it looks like this, right? So we were to talk about limits right here. So let's call this function right here f of x, okay? So this is just some random f. I don't know what it is. It's f, who cares? Now, the notation for one-sided limits. So the limit of f of x, as x approaches, like a little arrow, x naught or x sub 0, if it has a minus on it, that means we're talking about limits from the left. So this is left-sided, oops. This means left-sided limit of f. That is to say, the functional value that f is approaching as x approaches x naught from the left side. Just in words, right? Just we can visually see what's going on. So it says minus. We're approaching this value from the left side. Coming from this way. So the functional value meaning the y value. What the y value is approaching as it gets closer and closer to x naught. To get closer to this x value, what the y is doing? Getting closer to 1, right? You see what I'm saying? So as you approach it, if we approach so basically imagine I'm coming from negative infinity and just going all the way over here, getting closer and closer to x0. But the y values are changing depending on your x's, right? So as I get really close to this one, the y's go closer and closer to 1. So there's a hole there. So I don't actually get there, but I approach 1. Does that make sense? That's basically what a limit is. I can't always go there, but I can approach it and get infinitely close. So if the function appears to be going there as x gets infinitely close, then we say the limit exists at that value, but the function may not. So the function is undefined, but the limit exists. Okay, so all you have to do is just look at what is the y value as I get super close to x0. In this case, it's 1. So from the left, The answer would be 1. So similarly, for the right side, if they were to write f of x as x approaches x0 from the positive side, you'll see a little plus sign. So if you see a little plus on the x naught, that means we're coming from the right. What does the y value do? So look at this function here. As I'm coming from the right side, what are the y's approaching? 2. So your limit would be 2. That's all you have to do. Now the actual definition is really complex and deep, but visually and graphically, it's not that bad, right? It's right there. So this is called the right-sided limit of f of x. That is to say, the functional value that f is approaching as x approaches x0 or x naught from the right side. I'm being very informal, but it makes sense, right? So you would say it's just equal to 2. Nothing crazy. X not just a random x. But let me give you a graph where we can move the numbers around. They can see it. Give me a second. An interactive graph. Yeah. I move my graph over there. I purposely made this graph with a hole in it, so you can see what I mean. Although this will be a two-sided limit. Where is it? There. Okay. So here's my line. You can see right away that if I plug in -4 at the bottom, I'm going to have division by 0, right? I cannot plug in -4. But we zoom into -4, which is about here. So as I approach, move a little bit. As I approach -4 from the left side, right? What is the y value approaching? getting smaller, right? Or is it getting bigger and bigger? Yeah, so, but as soon as we get there, looks like it's going to 1. Looks like it wants to be 1 at -4. So, but as soon as you get there, it's undefined because there's a hole. But the functional values are approaching 1. So the limit is 1, but the function is undefined. From the right side, you say, okay, as I go closer and closer, -4 from the right, it's getting closer to 1 as well, right? So if the left and right limits are the same, that's when you say your limit exists. They have to be the same. In this example, if they would have asked what is a double side limit or a general limit, you would say it does not exist. But here it does, which we'll talk about in the next example in just a second. But do you see what I mean by limits? Does that make sense? Or you're just getting closer and closer and looking at the y values. That's it. Okay. Alrighty. Okay. So in order for a limit to exist, that is to say, the limit of f of x as x approaches x naught. So if they don't actually put a minus or a plus, then they're actually asking about the general limit. So that means you have to check. Is the left one the same? Is the right one the same? If they are, then you say yes. If they're different, you say it does not exist. Okay. The limit from the left must equal the limit from the right. That's it. If they don't, you say it does not exist. That's a weird arrow. Is that part clear? All right. So we'll call this example 1, I guess, or I don't know. So the question is, does the limit exist in example 1 at x naught? Do y'all think? Does not, right? Does. These would have to be the same thing. Yeah, this example here. So so the way we would explain it, right? In our own words. Well, you could put it in plain English if you want, but since the limit of f of x approaching x naught from the left is not equal to the limit of f of x as x approaches from the right, then the limit does not exist at x naught. Basically, it's like we're kind of like what's the word? That the function is hinting at a value, so we can kind of see it, like you can see it approaching something, but the function cannot accept the value, but we know it's technically going there, so we can like interpret like, yeah, it should be this, but it can't actually use it. Okay. So you use ideas of infinity to like approach it super close, like approaching it forever, and say, yeah, the function gets there and eventually, but officially it is undefined. But not always. It could be defined. It depends. So the limit could exist and the value could be there. It doesn't have to have a pole. Like for example, I don't know. Let's say it's right at 0, right there. Do you agree that the limit from the left would be 0 and the limit from the right would be 0, but it's also defined there? You see how that's not a problem? Or I could pick this point there. Right? If I go from both sides, it's defined, and I can plug it in. So all it is, what is a function approaching as your x approaches that value? In a nutshell, that's all the limit is. Okay, we're looking at the functional values as x approaches a specific number. Okay, so look at some of the homework problems. I think that's all you really need to start doing them. So let's look at them. So look at question 1 from your homework, H12.1. So they're asking determine, so this is F, is red line or whatever, or curve. As x is approaching 1, notice they don't have any symbols, so they're asking both directions. Like, determine the limit for the function f. The limit as x approaches 1 is going to be what? So they have to be the same in order for it to exist. So if it's not the same, you would put D and E or does not exist or undefined. But coming from the left, let's say I'm going to the 9, right? Like 9. 1, 2. Okay. So they're going to the left. I'm getting closer to 9, but I'm going to the right. That right would be way up top, coming this way. Getting closer to 9. So both sides will be 9. Do you all see that? So all you have to do is say, okay, well, the limit visually should be 9. Oops, I changed it. This one would be 3, I guess, right? 1, 2, 3. So as I approach from the left, it's 3. From the right, it's 3. 3. Yeah, there it is. The function goes to 3 as x goes to 1. That's what this arrow means, okay, from both sides. Are there any questions on that idea? Oops. Okay. So it's not too bad, right? So that'll be pretty much like your first first like weekend calculus one. Okay. So this kind of if you are going, this first chapter will feel intimidating, but it's not. It's if you see it visually, it makes sense. Then the chapter right after that, it gets easy again. And it's just as long as you do your algebra, you'll be good. So if you're good at algebra, it will be easy. If you're struggling with algebra, calculus will be challenging. You will have some freak out at all. Very little bit. This is unit circle. You go to Cal 2, freak out will come back to monster. But hopefully you'll remember it. -1. Oh, here, right? What is it? This is F. That is F. What is the limit? Looks like it's a one side, right? Can you see that? The minus sign on there? So that means I'm approaching -1 from the left side. So where's the function approaching as I get closer and closer to -1? What's the y value?
That 4.
1, 2, 3, right? So this would be 3. Yeah. From the right, what is it? Approaching the same number, right? Going closer and closer to -1. The y value is still 3, right? So now it has no symbol. So this is 3, this is 3, so this one has to be 3. It exists. Then it asks you, okay, well, can you plug it in? Is it defined? Or is there a hole at -1? There's a hole there, right? So you cannot do f of -1 because it's not defined. Is it defined elsewhere? There's a dot, right? So you would plug in that value. So f of -1 is actually 4. But the limit is 3. So plug in this stuff accordingly, you'll be good. You see that piece right there. Okay. Anyway, any questions on example 2? Is that clear? Okay. Just remember, they're going to give you like hardcore definitions, and it's going to seem complicated, and it is. The theory itself it's complex, but the work itself is not. Okay. Number 3. Let's see here. Same type of deal, but I can't see that thing. Let's look at this one. Given the graph, find the following limits. Okay. So this whole thing is f. As x approaches 1 from the negative side. So here's 1. So as I approach from the negative side, I'm going to what value?
5.
Yeah, it looks like 5. If I approach from the right, positive 1. Like 1's right there, right? So the approach from the right, what is y going to? Yeah, it's gonna be 0. So just plug them in, you'll be good. Are they the same? So you would put D and E for number 3. The two sides are not the same. Okay, it's not exist. And then check, can I plug it in? Is there a defined point for f of -1? Or is there a hole? It looks like we have a point there, but a hole here. So you would use this number, not the bottom one. Yeah, the y value, because you're plugging in -1. So where is a function at -1? Here, not there. Sorry. I think it's positive, right? They said negative. Oh no, this is a different one. There it is. Positive. Sorry. So 1, negative, one positive. So they are different. So the actual limit will not exist. Okay. That's pretty much it. Number 6, I'll make you sketch this guy out. They don't give you the picture. Okay. There's something else I forgot to mention. So if you don't have a graph, right? So far we've had graphs. First thing you should do is just plug it in. And you go to 4. For this example, x is approaching 4. What is this function doing? Plug it in and find out. So if you get a value, then that's it. That's your limit. You can also graph it and see, okay, what's happening at 4, right? Just look at the graph. If you plug it in and you get an error or undefined, that means you can't plug it in, but it might exist graphically, so you got to check it. So there's 2 ways to do this. You can use the graph like we've been doing, or you can do a numerical approach. In this case, numerically and graphically. We've been doing graphically this whole time. Numerically would mean we plug in numbers super close to 4, right below, right? 3.9, 3.99, 3.999. Keep doing that. Then you try 4.01, 4.001, super close, and see on the calculator, are those numbers approaching the same thing? As they get closer and closer, it should be the same as the graph. You know, as I plug in numbers really close, I should get a limit. If they are different, you would say it does not exist. Graphically is the easiest way to do it. In my opinion, I would just do that. I don't know if they're forcing us to do numerical here, but let's see. Here they force us. Number 10. So they want to know. I need to fill in the blanks. I guess not, but this will help us understand what I'm saying. So if I'm not looking at the graph, I want to see what is the function doing this against. Go to as the let's say y, so the independent variable goes to some number. In this case 8. But coming from the right side, right? It's super close. Where is the function going to? Just plug them in here, right? It should calculate. Then on the left side of the graph below, closer to 8, it takes some other values. If it's the same, you just apply that. What is it going to? All you have to do. And I'm not going to test you on any of this. You don't have to do it numerically, but you will in calculus. Okay, so I would say try it once, see what I'm saying. Put in your calculator, just to look at it. Is this one forcing? Okay. Well, it was an idea of infinite limits. So we're not going to a specific place, we're just going to keep going to the right. Positive infinity means to the right. So look at this function. As I approach positive infinity, right, which is all the way over here somewhere, forever, what is the graph doing? What are the y values approaching? As x gets bigger, right? One and barrier 1. So as x is big, I'm going to 1. Eventually, if x is infinitely large, right? The function will go 1. If I go to negative infinity, it will also go to 1. Same thing with like division by 0. You can't plug in 0, but you can approach it with limits. So we use this idea to deal with division by 0. Okay. for example. Quickly grab it. Excuse me. Let's say we had this made up function. Right. We know we cannot plug in 0. Yeah. But if I approach 0 from the right side, function shoots off to what? Shoots upward forever, right? They come from the right. I approach 0. The function goes to infinity. If I approach from the left, it goes to negative infinity. The limit doesn't exist at 0. It's also undefined there, but we can look at what's happening on one or the other side. You can do one-sided limits, but they're technically infinite limits. Okay, so that can happen. When you're finding a limit, it could be infinite. I don't know if you'll see that here, but maybe. They start talking about infinity a little bit. Like part C and D. You're approaching 7. So what happens when you go to 7, right? It shoots off from the left and the right. So both sides are going to infinity. So the limit would be infinite. So I would argue it exists, but it's infinity because they're the same. So yeah, just type infinity or minus infinity. Okay. But anyway. Is there any questions on limits? Does that idea make sense? Like the big picture? I don't know if we have time for anything else. So. Okay. All right, so last thing we did 1920 and accidentally skipped 18, so we did 18 today. So let's look at 21. Go from there. Okay. So this is back to like college algebra stuff. It's finding domain range given different functions. Last time we did quadratics, right? On Monday. So here they start talking about rational functions. You remember how to find a domain of a rational function? Or any function. Well, let's do it on paper. I'll just copy this down and we'll do it. So example 1, find the domain. It's problem 1 from the homework. Of f of x equal to x squared plus 9x plus 18 x squared minus 2x minus 15. Okay, so for any function, when you're looking for domain, you want to ask yourself, what are the values that you're not able to use? You're kind of looking at it backwards. So what's not okay? And then work around that. Okay. So when you see irrational, the thing you should be thinking about is division by 0 is not okay. And that's probably the first thing that's going to happen, or first thing you need to look out for. So find out, does this thing ever have a value that makes it 0 on the bottom? So step 1, set the denominator to 0. So the question is, like, when is this equal to 0? Well, solve for it and you'll know, right? And then you're going to want to avoid those numbers. So it may create a domain around those problems. Okay. So does this factor pretty or no? Okay. Looks like it's gonna come out nice, right? -5 plus 3. Yeah. Okay. So that means set this guy equal to 0, set this guy equal to 0. So those are the two issues, or two problem areas. The way I like to do it is make a number line. So you know what? Let's say -3 is somewhere over here. 5 is over here somewhere. These are holes that I cannot deal with. So create the domain around those problems. So how would you write all the numbers above 5 in interval notation? You remember? Well, you put first of all, we have to put parentheses on 5 because we cannot include it. Then you'd say everything after 5, meaning everything until infinity. The middle part would just be from -3 to 5, right? But parentheses because they're problems, I do not want to include them. Everything below. How would you write everything below? -3. Yeah. -infinity to -3. Okay, so the domain, the answer, it's just these 3 pieces. It's glued together. Glued together with a union symbol. That's what union means, right? You're combining different sets together. But in plain English, you would say the domain is everything except -3 and 5. But in interval notation, you would write it this way, which is what they want. This is step 2, by the way. Use a number line. Around x equals 5 and x equals -3. Okay. Any question on example 1? You remember now? Okay. So two then. Look at number 2. Same question. Find the domain. Vertical asymptote and horizontal asymptote. Remember how to find asymptotes. Yeah, where we have a 0 in the denominator. So that'll be a vertical line. Horizontal has like 3 cases. Horizontal is the annoying one. So I'm probably gonna do it on a different page. Let me find the notes just to give them to you. Here it is. I'm just gonna send them to you, save you some writing. Give me a sec. Okay, so this is what I just sent you. These are the rules for asymptotes. Basically, you set the denominator equal to 0. So that's what we just did. Whatever solution you get, that answer they're calling K, x equal to that number, K, would be the equation of your vertical asymptote. So if you have more than one, then you'll have x equals, like in our case, x equals 5 is an asymptote, vertical, x equals -3. So the actual line equation, not the value. I'm not saying the number 5, I'm saying x equals 5, the equation. Okay. So this is really the software corrects set we just did. The horizontal is a little different. There's 3 cases, so it depends on the degrees. So n is the degree of the top, b is the degree of the bottom, the numerator and denominator. So if the numerator has a smaller degree, the degree in the bottom is bigger, then your asymptote is y equals 0. Y equals 0, and that's it. If they are the same, you look at the number on the biggest power, the coefficient on top and bottom, and just divide them. The y equals whatever that number is into your horizontal. Number 3 is the factoring one. If the degree on the top is bigger, you will have to do long division. Well, then your figure is flat. Okay. So, well, hopefully it's just mainly me, but if this happens, life sucks. Gotta deal with it. Yes. Yeah, the degree of the degree means the highest power. All right, so let's look at this question again. They didn't ask for it, but if we go back right here. What's the degree of the top? And the bottom? So they're equal. So that's case 2. Yeah, you have to divide. So what is the coefficient on the highest power? What is the leading coefficient? We talked about that Monday. What is the leading coefficient of the top? And the bottom? Yeah, they're both 1, right? So you just take the 1, divide by 1, which is 1. So y equal to 1 would be the horizontal asymptote for example 1. They didn't ask for it, but that's what you would do. Vertical, we did the work for the vertical, but they didn't ask for that. We were just doing domain. But you could have done both at the same time, right? So I'm gonna do example 2 on the next page, using those ideas. All right, where is that question? All right, so example 2, let f of x equal 10 over x plus 10. Find the domain. I don't have enough space. Vertical and horizontal asymptote. Okay. So to find a domain, what is the first thing we do? Yeah. So to find domain, and technically vertical asymptotes. Set the denominator to 0. Oops. Okay. So that's pretty easy, right? X is -10. That is the only problem area that we have. So draw your vertical line. No, sorry. A number line. Use a number line. To help you find the domain. So I only have one problem in the middle. So how would you write everything below -10? Yeah. Everything after 10. -10. So just combine these two pieces and you're good. Any questions on domain? Is that okay? All right. vertical asymptote. The vertical asymptote happens wherever should I phrase that? An X value causes division by 0. So which causes division, which number causes division by 0? Yeah, so the answer, vertical asymptote. So I'm gonna put VA is X equal to -10, the equation, not the number. Yeah, that's our K. The vertical line X equals -10 is like a barrier that the function can't cross. Because it's undefined. We can get infinitely close though, right? Never touch it. Determine which case you have. By looking at the degrees of the numerator / denominator. Okay. What is the degree of the numerator for this example? It's the degree of the top.
1.
Is there an X up there? So if there's no X,
It's not.
what would the degree be? Yeah, it's going to be 0 if there's no X. The X to the 0 would be 1. So you could technically put 10, it's there. Okay. But it's not. The degree of the bottom. So which one's bigger? So based on that PDF I sent you, if the degree in the bottom is bigger, the horizontal asymptote will be y equals 0. You have to put y equals. So the horizontal line y equals 0 is the horizontal asymptote. I don't see any I'm hoping right a bit. There's no case 3 in your homework. If the power is bigger on top, then you got some problems. I would first try to factor and see if you can just cancel. But if you can't, you have to do long division. There's no choice. And then that can be annoying But it looks like you can factor all of them and avoid it. So I think you'll be good. You might have to do it in calculus, but I think here you're good. Let's see. Yeah, I think I didn't use it until Cal 2, long division. And then you learn it in high school, you use it maybe once in college algebra, then it becomes useful in Cal 2. So, but yeah, I don't think you have to do it here. But just keep that in mind. But yeah, all the rest of the questions are the same thing. There's only one extra idea I want to show you, and we're done. Call it a day. Okay, so at the very bottom, as you can see, it's the same thing over and over again. Domain, asymptote, domain, asymptotes, who cares? Here they talk about kind of like limits, basically, but before you actually do limits, they phrase it this way. But here, intercepts, you know how to do that. Removable discontinuity, so that's a calculus idea. So basically that means there's a hole that can be filled. So if you graph this, technically this will cancel with one of these. The fact at the top, you get x plus 10, x minus 10. So that'll cancel one of these. So technically it's undefined at 10, but because they cancel, you consider that a removable discontinuity. You are and x equal to 10 because that cancellation happens. So usually it's viewed to say it's not continuous there. And there's 3 requirements for continuity. I don't think they really ask about it, but the requirements is that the function is defined there, the limit exists there. Okay, so limit has to be the same on both sides. Yeah. Just a number. It'd just be 10. So the one that cancels out is the one that's removable. So the top of different squares. X minus 10 cancels, so that's the one that was removed. After this, calendar, this should cancel. Like this one. So it'd be again the same. It just happens to be x equals to 10 again. Okay. So that's all you have to do for removable. That's the only thing we didn't talk about. But I think that makes sense, right? Okay. Right then, we'll stop here, I guess. You take roll and work from there. Huh?
What things would you want to do?
What was that?
What would be meeting Monday?
Yeah, I think